The first thing we're going to learn today how to graph or how to find the vectors and lines on the planes. Now we're going to write down the equations. We're going to start with lines in R2, and then we're going to do it on R3. The only difference is going to be 3 dimensions here and 2 dimensions here. So for example, that's what we need to know. So here's a line, and here's the vector x. We need to know there's a vector, it's called the normal vectors. It's going to be always perpendicular or orthogonal to the vector x. And there's another vector, it's called d, which is the direction vector for the vector x. You check that when we do the example, because now they just explain that to you. And you see this, the normal vector n is always the dot product between the vector n and the x, always 0 because it's orthogonal. We already learned what's the meaning. Like for this example, they give you the vector and the normal vector, which is 2, 1. And the vector x with x coordinate and y coordinate, the multiplication between n and x is going to be 0. This is called the normal vector. It's always orthogonal to the vector x or to the line. So here's the thing. X is a vector on the line. N is a normal vector which is orthogonal to the line and orthogonal to any point on the line. Okay? You can check that. Next slide. Here's the definition. The normal form of the equations of the line L and R2. That's what we're going to use if they ask you to write down the equation. This one. Do not use this one. Just n dot product with x minus p. P is a point on the line. N is a normal vector which is orthogonal to the line. And x is the vector. So where p is a point on the line, L, and n not equal to 0 is a normal vector. Because if n equals 0, everything is going to be 0. We can't write down the equations. So always the normal vector n, always not equal to 0, is a normal vector for L. That means it's orthogonal to L. The general form of the equations L is going to be this one. A and B and C are, or like if they ask you to write down the general form, you can write down this form first, and then when you simplify it, it's going to be the general form. So here's with the general form, the normal vector is AB. So let's plug in here. The normal vector is AB. That's me. I'm going to do the steps here. So AB times x, which is xy, is the vector, minus, let's say the point B, let's choose another 2 vectors. Here, let's say C1 and C2. Equals 0. So now we're going to extend that. I'm not going to do the product first. I'm going to do the difference. So it's going to be the normal vector A, B, write down these steps. Now the difference is going to be another vector, which is x minus c1 and y minus c2 equal 0. Now let's do the dot product. That means a times this one and b times this one. So it's going to be a times x, that means ax minus ac1 plus bx, sorry, by minus bc2 equals 0. That's mean ax plus by equal ac1 plus bc2. Check this part, it's all just a number. Because a is from the normal vector, which is a number. B is from the normal vector, which is a number. C1 and C2 is a vector, that means this is a number and this is a number. So when everything here is going to be just the C. That means it's going to be ax plus by equals C, which is exactly the same thing here. This is just to show you when they give you example and they ask you write down the normal form of the equations in the normal form. So when you're done from this one, and if they ask you to write down the general form, just simplify this one and you're going to get the general form. We're going to check that when we do an example. Okay? So this is how to prove that this is the general form of the equations. The vector form. If they ask you to write down the vector form of the equations of the line in R2 or R3, this one is going to be the vector form. X equal is the vector xy. In R3 is going to be xyz. P is the point. T is just a scalar. D is the direction vector. So if they ask you to write down the vector form, in this case, we need the direction vector. Direction vector is going to be a vector for L in R2 or R3, like a vector parallel to L. For example, here's the line, L. This is the point P. The direction vector, let's choose another point here. This is going to be the direction vector D, which is a vector parallel to the line. The normal vector is going to be like here. It's going to be perpendicular to the line or to the direction vector. Okay? This form, when we extend this form, is going to call parametric equations of L. That's what they asked the students last semester. They give an example and a question. Write down the parametric equations. That means you're going to use this form, and I'm going to show you how you're going to write down the parametric equations when we do an example. Okay? But now we're going to do that in R3 and the planes. It's not a line. So instead of line, we're going to study plane. That means this plane could be XY, this could be YZ, this could be XZ. Okay, 2 dimension, it could be XY. So it's a plane in R3. And we need to find the equations for this plane. This is the normal form. N, which is the normal vector, It's going to be A, B, C, because it's in R3. P is a point. That means this point is going to be 3-dimensional. They're going to give you the X and the Y and the Z. So it's going to be X, Y, Z. And not equal 0 is a normal vector for the plane. The same thing, when you have this form, extend that, simplify it, you're going to get the general form. How are you going to simplify it? By multiplying, do the dot product between n and the difference between the vector and the point to get exactly this form. And you see X, Y, Z, exactly the same steps when I did for the line is going to be for the, and move all the numbers to the other side. Just keep AX, BY, and CZ on this side. Everything here on this side is going to be a number. That's why here they just assume it T. So this one is going to be the general form. So here's the important thing. They're going to give you the equations of the plane. They're not going to give you the normal vector. So if you look to the general form, the normal vector, here is the A, here is the B, and here is the C. So from the general form, you can find the normal vector, A, B, C. Okay, so this is important. If they give you the normal vector, you're just going to plug in A, B, C here. It's going to be this side of the general form. Now we just have, we're not going to do an example here, but there's questions on website. They're telling you to find the distance between any point and a line. It's going to be the distance between a vector V and the projection of vector V to the direction D. This is a vector. Okay, this is not a distance. This is called the distance between the point and the line. Here's a line, L, and here's the point P, or B here. To find the distance between the line and the point B, we need to find a vector. How are we going to find the vector? By saying this is another point, let's say Q, and here's the point P. So we're going to find the vector V. The vector V is here. To find the distance between this point and the line, we're going to find, here's the vector V, the projection between, for the vector V on D. We're going to do that in details when we do the last example today. What's going to be the projection? You're going to ask me the distance between B and the line is going to be the general form over the length of A squared plus B squared. I'm going to do an example of details to show you how to find the distance between a point and a line. Because you're going to study these in details when you're doing calculate.